What if I told you that just by looking at a polynomial's coefficients, you can predict information about its roots without actually solving the equation? This might sound like magic, but it's actually one of the most elegant relationships in mathematics. Today, we're going to uncover these hidden connections that have been helping mathematicians for centuries. Root coefficient relations reveal the deep connections between a polynomial's coefficients and its roots. These relationships allow us to extract valuable information about solutions without lengthy calculations. Before we dive into these relationships, we need to understand the key components. A polynomial is a mathematical expression with variables raised to different powers, each multiplied by coefficients. The coefficients are the numbers that multiply each term. Here, an minus 1, down to a0 are all coefficients. These numbers completely determine the polynomial's behavior. The roots, also called zeros, are the values of x that make the polynomial equal to 0. When we substitute a root into the polynomial, the entire expression equals 0. Now here's where it gets fascinating. There are precise mathematical formulas that connect these coefficients directly to the roots. These are called Vieta's formulas, named after the French mathematician François Vieta. For example, in a quadratic equation, the sum of the roots equals negative b over a, and the product of the roots equals c over a. This means we can find information about the roots without solving the equation. These relationships extend to polynomials of any degree. The higher the degree, the more intricate the relationships become, but the underlying principle remains the same. Understanding these connections gives us powerful tools for analyzing polynomials efficiently. In the upcoming sections, we'll explore these relationships in detail, starting with quadratic equations and building up to higher degree polynomials. You'll learn how to apply these formulas to solve complex problems quickly and elegantly. Now we'll explore one of the most elegant relationships in algebra, Vieta's formulas for quadratic equations. These formulas create a direct bridge between the coefficients of a quadratic polynomial and its roots. Consider a general quadratic equation in standard form, ax squared plus bx plus c equals 0. Here, a, b, and c are the coefficients that completely determine our quadratic polynomial. Let alpha and beta represent the two roots of this quadratic equation. These are the values of x that make the equation equal to 0. Vieta's formulas give us two powerful relationships. First, the sum of the roots alpha plus beta equals negative b divided by a. Second, the product of the roots alpha times beta equals c divided by a. Let's work through our first example. Given the quadratic equation 2x squared plus 6x minus 8 equals 0, we need to find the sum and product of its roots using Vieta's formulas. First, we identify our coefficients, a equals 2, b equals 6, and c equals negative 8. Now we can apply Vieta's formulas directly. For the sum of roots, we use alpha plus beta equals negative b over a. Substituting our values, negative 6 divided by 2 equals negative 3. For the product of roots, we use alpha beta equals c over a. Substituting negative 8 divided by 2 equals negative 4. For our second example, we have the equation x squared minus 5x plus 6 equals 0. We're told that one root is 2, and we need to find the other root. Let's solve this step by step. First, we identify our coefficients. A equals 1, b equals negative 5, and c equals 6. Next, we use the sum formula. Alpha plus beta equals negative b over a, which gives us negative 5 over 1 equals 5. Since we know one root is 2, we can substitute 2 plus beta equals 5. Therefore, beta equals 3. The other root is 3. Our third example shows how to construct a quadratic equation when we know properties of its roots. We're given that the sum of roots is 4, the product of roots is 3, and the leading coefficient is 1. We can use Vieta's formulas in reverse. Since the sum of roots equals negative b over a, and we know the sum is 4 and a is 1, we get b equals negative 4. Similarly, since the product of roots equals c over a, and we know the product is 3 and a is 1, we get c equals 3. Now we can construct our quadratic equation. With a equals 1, b equals negative 4, and c equals 3, our equation is x squared minus 4x plus 3 equals 0. We can verify our answer. The roots of x squared minus 4x plus 3 are indeed 1 and 3, which have a sum of 4 and a product of 3, confirming our solution is correct. Vieta's formulas for quadratic equations provide us with powerful tools. These two simple relationships allow us to find sums and products of roots without solving the equation, determine unknown roots when given partial information, and even construct quadratic equations from root properties. Now that we've seen Vieta's formulas for quadratic and cubic polynomials, we can discover the beautiful pattern that extends to polynomials of any degree. This generalization reveals the deep mathematical structure underlying all polynomial equations. Consider a general polynomial of degree n. We write it in standard form with leading coefficient an, followed by terms of decreasing degree down to the constant term a0. This polynomial has exactly n roots, which we'll call r1, r2, up to rn. These roots may be real or complex numbers, but they completely determine the polynomial's behavior. Before we generalize, let's recall the patterns we discovered. For quadratic polynomials, we had two relationships. For cubic polynomials, we had three relationships. The pattern is becoming clear. Notice the alternating signs: positive, negative for degree 2, then negative, positive, negative for degree 3. This alternating pattern continues and is captured by the expression -1 to the k power. Now we can state the general Vieta's formulas. For a polynomial of degree n, we have n different relationships between the roots and coefficients. The first relationship involves the sum of all roots taken one at a time. This equals -1 to the first power times the coefficient ratio. The second relationship involves the sum of all products of roots taken two at a time. This equals -1 squared times the appropriate coefficient ratio. The third relationship involves the sum of all products of roots taken three at a time. Notice how the pattern continues with -1 cubed. This pattern continues all the way down to the final relationship. The product of all n roots equals -1 to the n power times the constant term divided by the leading coefficient. We can write the complete general formula compactly. For any k from 1 to n, the sum of all products of roots taken k at a time equals -1 to the k power times the ratio of coefficients. These relationships are called elementary symmetric polynomials in the roots. They capture all the essential information about how the roots relate to the original polynomial's coefficients, regardless of the degree. The power of this generalization is remarkable. Whether you're working with a quadratic, cubic, quartic, or even higher degree polynomial, these same patterns apply. The alternating signs and coefficient relationships hold universally. Now we'll work through our second example, which demonstrates how to construct a polynomial when we know its roots. This is the reverse process of what we typically do in algebra. We are given that a polynomial has three roots: -1, 2, and 3. Our goal is to find the polynomial equation that has these specific roots. Let me clear the screen so we can work through the solution step by step using the factor theorem. Step 1. We apply the factor theorem. If r is a root of a polynomial, then x minus r is a factor of that polynomial. For our roots -1, 2, and 3, we get the factors x minus -1, x minus 2, and x minus 3. Notice that x minus -1 simplifies to x plus 1. Therefore, our polynomial in factored form is p of x equals x plus 1 times x minus 2 times x minus 3. Now we need to expand this factored form to get the standard polynomial form. Step 2. We expand the factored form. I'll multiply the first two factors together first, then multiply by the third factor. First, I'll multiply x plus 1 times x minus 2 using the FOIL method. Using FOIL, x times x gives x squared, x times -2 gives -2x, 1 times x gives x, and 1 times -2 gives -2. This gives us x squared minus 2x plus x minus 2. Combining like terms, -2x plus x equals -x, so we get x squared minus x minus 2. Now I need to multiply this result by the third factor, x minus 3. Next, I multiply x squared minus x minus 2 times x minus 3. I distribute each term in the first polynomial to each term in the second polynomial. This gives us x cubed minus 3x squared minus x squared plus 3x minus 2x plus 6. Combining like terms, -3x squared minus x squared gives -4x squared, and 3x minus 2x gives positive x. Our final result is x cubed minus 4x squared plus x plus 6. Let me verify this result using Vieta's formulas to make sure our expansion is correct. Step 3. Let's verify our result using Vieta's formulas. For a cubic polynomial ax cubed plus bx squared plus cx plus d with roots r1, r2, and r3, Vieta's formulas tell us three relationships. Let's check. The sum of our roots is -1 plus 2 plus 3, which equals 4. This should equal negative b over a, which is negative 4 over 1, or positive 4. Check. The sum of products taken two at a time. -1 times 2 is -2, -1 times 3 is -3, and 2 times 3 is 6. Adding these, -2 minus 3 plus 6 equals 1, which matches c over a. Check. Finally, the product of all roots, -1 times 2 times 3 equals -6, which equals -d over a, or -6 over 1. Check. Perfect. All of Vieta's formulas check out, confirming that our polynomial x cubed minus 4x squared plus x plus 6 is correct. This demonstrates how we can construct a polynomial from its known roots using the factor theorem and algebraic expansion. We've covered a lot of ground in our exploration of root coefficient relations in polynomials. Now it's time to bring everything together and see how these powerful concepts apply to the real world. First, we mastered Vieta's formulas. For quadratic equations, we learned that the sum of roots equals -b over a, and the product equals c over a. For cubic equations, we extended these relationships to include the sum of all roots and their product, connecting them directly to the polynomial's coefficients. And we generalized these patterns for polynomials of any degree, giving us a universal toolkit for understanding the relationship between roots and coefficients. Now, you might be wondering, where do we actually use these concepts in the real world? The applications are more widespread than you might think. In physics, root coefficient relations help us analyze quantum mechanical systems, solve wave equations, and understand oscillatory behavior in everything from pendulums to electromagnetic fields. Engineers use these concepts extensively in control systems design, signal processing, and stability analysis. When designing everything from airplane autopilots to audio equipment, these relationships are fundamental. In computer science, polynomial root relationships appear in algorithm optimization, computer graphics for curve fitting, and even in machine learning for polynomial regression models. The beauty of mathematics is how these abstract relationships connect to solve real problems. But what should you remember most from our journey together? First, remember that root coefficient relations reveal deep, beautiful connections in the structure of polynomials. They're not just formulas to memorize, but insights into how mathematics works. Second, Vieta's formulas give you powerful shortcuts for solving complex problems. Instead of finding roots first, you can often work directly with their relationships. Third, these concepts beautifully bridge pure mathematics with practical applications. What seems abstract in the classroom becomes essential in professional work. Finally, understanding these patterns helps you develop mathematical intuition that will serve you well in tackling new challenges throughout your mathematical journey. Mathematics is a journey of discovery, and you've just mastered one of its most elegant and useful concepts. You now have the mathematical tools to tackle polynomial problems with confidence and deep insight. These concepts will serve you well in advanced mathematics and beyond. If this video helped you understand root coefficient relations, please give it a thumbs up. Leave a comment if you have questions or suggestions for future topics. And don't forget to subscribe for more mathematics tutorials that make complex concepts clear and accessible. Keep exploring, keep learning, and remember, every mathematical concept you master opens doors to new understanding.